Zaproszę na scenę kolejnego gościa, który poruszy wątek dotychczas nieporuszany podczas Stormwater Poland 2026, a mianowicie wątek gleby i zdolności infiltracyjnych gleby. Jak istotne są dane o wilgotności gleb w przewidywaniu powodzi? O tym będzie opowiadał Dominik Kolesch z Okeanos Smart Data Solutions.
Hello, thanks very much for having me here. I'm very honored to be a speaker on this big stage. I'm Dominik from a small engineering and software company from Western Germany. And what we mainly do is create models for flood prediction. And today I want to show you our approach towards this. When we started off, we were looking at the water cycle and we were basically like, okay, what is actually leading to floods? And of course, as you all know, rain is like the most important component. And additionally, in the water cycle, we have a second important component, the soil moisture precondition, which if the soil capacity to infiltrate is already used up, we have a much higher probability of floods if heavier rain events arrive. Of course, there's a lot of other parameters contributing to flood risk. Oops. The whole situation on the ground is important as well, like the digital elevation model, what land use, how much surface is sealed in the area, how much of the actual rainwater will run off on the surface and contribute to local floodings, but also river floodings. For that, you need a lot of data, like the river channel cross-sections, for instance, to be able to model flood in a precise and in a validatable way. And so especially in smaller catchment areas, we have the problem that this kind of data is often not available. That's why for flood prediction, we went with another approach, a purely data-driven approach. Of course, making those flood maps and using those models, those calibrated models for planning purposes, for flood mitigation purposes is very important, but as I said, for flood prediction, they are not really suitable. So we looked at what data we can get already. This is, for instance, the precipitation data of the weather services with their weather radar systems, the precipitation prediction, which is very important. And then, of course, the components I was talking about already, like water level in the rivers, soil moisture data, and in some cases also local precipitation sensors. So when we set up our systems, we always have to set up sensors first so that we have a reliable data source for our predictions. But as long as no data has been collected, the only thing we can basically do is have like threshold values set for certain water levels and then give an alarm in case things are happening. This is not really a prediction, but without sophisticated training with longer time series of data, you cannot really have any prediction value. So, but after we collected some data and we are able to set up our models to do pattern analysis in the data, the relationship of the different components, and then use different models to find the most suitable predictor. Of course, sensors are not cheap, and if we require to set up sensors in like smaller municipalities, they are usually very cost sensitive. They don't have much money for flood protection or flood prediction. So we are always looking at like the most optimal approach to like set sensors in certain, at certain key areas, at neuralgic points in rivers and streams where floods are actually happening or where the streams are actually contributing towards floods further downstream. Luckily, in the recent years, sensor development has made some huge moves, especially in terms of energy efficiency. So new data transmission technologies have been coming up that sensors can really work without much intervention, let's say. And with IoT data transmission protocols reduce the energy impact on the sensor a lot. So we can have sensors in the field for like longer time periods without having to tackle them directly. Yeah. So, as I said, we use water level sensors in streams, which is the most important component. We have soil moisture sensors in the most representative soils within the area, which we calculate before. And of course, the radar rain data is very important. When we set up such a sensor network, we look at the different catchment areas. Find like the most suitable points, looking at like flood-prone areas, and then go back into the rivers and stream, which, as I said, contribute the most water towards them, to be able to monitor the whole area in a sufficient way. And in this example, for instance, we have a huge area of 85 square kilometers. We installed 15 water level sensors, additionally 8 soil moisture sensors, and included sufficiently precise water level sensors which have already been existent in that area, and started to train our model. So the interaction between different measurements is not always super clear. There's time lags. There's, of course, if you look at on the right, the different soil moisture sensors, there's different values. So it's very hard like to make patterns out of it by hand. You can do some statistics, but that's why we use machine learning models to be able to identify, or that the model is able to identify patterns, and with more and more time and more data, gets more robust, and being able to depict the essential informations from the data we have. So here you can see our different model approaches. We have two machine learning classifiers. First is an isolation forest, the other one is a boosted regression tree. It's not like the big brain AI we were just hearing about. It's fairly simple models, but we also want to have like a cheap and or affordable and a reliable flood prediction software in the end. So and with those models we made some good results. So on the right you can see on top the water level measurements, in the middle the soil moisture measurements, and in the bottom the precipitation. And all the areas which are marked in red is when our system alerted the user. And the dotted lines, the black dotted lines, depict the area where the water level thresholds were actually exceeded. So we had some lead time toward the event with our alarm, and almost stayed active. The alarm almost stayed active until the whole wave went through. So I have some other examples for some other data plots for our prediction model. So here you can see in the bottom that with a predicted precipitation of a persistent rain event, we had like a first alarm value, but it has been dismissed after a couple of hours because the rain prediction changed and went down and so the alarm was dismissed. But then after 2 more hours, there was a peak in soil moisture detected, and there was also some rain predicted in the future, so the alarm went off again, and so we had like a lead time of approximately 8 hours towards this big event. For heavy rain events, it's a little more tricky, as they build very quickly and rain down very quickly as well. So here we can see that we reached approximately 45 minutes of lead time towards this event. It's mainly based on the relationship between the rain and predicted outcome in the water levels of the monitored stream. To answer the question whether soil moisture is a relevant parameter in flood prediction, I brought a case study with me. So for now, we only saw some slight implications that it might be important, but we wanted to do a thorough analysis. So we used one of our case studies where we have set up our system the longest. It's in the very west of Germany, in Saar Louis. The Saar River flows through the area, and it has several tributaries coming into it. The Saar River itself is very well monitored and not a problem, but the tributaries are the ones who cause local floodings. And so that's why we installed sensors, monitored them, included the existing sensors there, and trained the whole model after we had 1 year of data. We managed to improve warning times depending on the type of event. For 45 to 90 minutes for heavy rain events, and 1 up to 8 hours for the so-called persistent rain events. After the 2nd year of collecting data, we retrained the model, and now I want to show you the different results between a model with soil moisture and without soil moisture. So here you see a time-stepwise analysis of the same values in both models. So like in the top left, there is a soil moisture model, say 0, model without soil moisture, say 0, and a simple confusion matrix. And as you can see in the 2 brackets with false negatives, false positives, we have a difference between those 2 models. So in general, we saw that the model including soil moisture produces a lot more alarms than the model without considering soil moisture. And we were thinking about why that is, but because we looked at a time-step-wise analysis of in the comparison of the different models, we figured that it's because the tails of the active alarm values were way longer with the included soil moisture than without. You can see it here on the graphs on the right. This is a model including the soil moisture data, and you can see like after the dotted line ended, so the exceedance of the threshold value for the gauges ended, the warning period was still ongoing. And that was because the soil moisture after a rain event, of course, rises. And with an elevated soil moisture, you have like a higher risk of flooding if there is a new rain event coming. So in this case, we just need to change like our UI in the front end to be able to tell the user, okay, we have elevated soil moisture. If there's rain coming, there will be probably a new alarm value, but for now, it's probably fine. To come back to my initial question whether soil moisture data is overlooked in flood prediction, I want to say that it can, in certain cases, be very important for flood prediction, but in most cases it doesn't make much of a difference. But we cannot really neglect the data as it is important in the hydrological process, and especially in bigger catchment areas, it can contribute a lot towards how a flood can build out and how big the danger could be. In general, we tested our model in like several regions already. It's already applied in several regions. We made very good results with it, so data-driven flood prediction works very well, and we will continuously to improve our models. But as like a general conclusion, I can say the most important correlation is still between rainfall and water level in the streams, and with this and the soil moisture, we will move on to improve our models. That's it so far. Thank you so much for your attention.